So now that we have LP spaces as our quintessential example of Banach spaces, we can start doing some linear algebra on them. So we are going to study continuous linear map between LP spaces. Now in doing that, there is a tool that is extremely useful called interpolation. Now in a nutshell, what interpolation does for you is that it allows you to prove continuity of a map from LP to LP, a linear map from LP to LP, or not even linear, or sublinear, for instance, works well too, in an entire interval of values of P, as long as you have information about what happens at the endpoint of that interval. And the information you need at the endpoint is not even continuity at the extreme values of P in your interval. You can have something a little weaker than continuity called weak type PP, which we'll discuss in a minute. So typically you would prove something like the fact that your map is bounded on L2, and then you have all of Hilbert space theory that allows you to do that, and you would prove something weaker than being bounded on L1, something called weak type 1,1, and interpolation will allow you to conclude that your map has to be continuous on all the LP spaces for P strictly between 1 and 2. So this is very useful in practice. Now, let me make all of this a little bit more precise. What is weak type? So we're looking at a map, not necessarily linear, not necessarily defined on all of LP. It's usually only defined on a dense subset. Typically, the C-infinity compactly supported function, which will form a dense subset of all the LP spaces, except L-infinity. You're asking for something that's a little bit weaker than being bounded on LP. So you're asking not for a control of the LP norm of TF, but a control on the measure of the set where TF is greater than alpha. And what you want is you want the measure of that set, let's say if F has LP norm 1, to decay like alpha TD minus P. Right? And if you have that, you say that your map T is weak type PP, and you denote it as T is a bounded map from LP to weak LP. And weak LP is denoted by LP comma infinity. We won't really talk about that as a space, but the idea is that you could use that to define a topology. I've excluded the case P equal infinity, where this definition wouldn't make sense as written. What we call weak type infinity. Infinity is just boundedness on L infinity, right? So the set of map, definitely the set of map that are bounded from L infinity to weak infinity is just a set of maps that are bounded on L infinity. Now I'm using this notation, and there's a bit of an abusive notation here if my maps were to not be linear, but in this course we will be focusing only on linear maps. Okay, now I'm saying that this is weak type, that this is weaker than being LP bounded. Let's just have a little proof of that, and then we'll see what the theorem is telling us. If you have a map T, which is, let's say, a bounded linear map on LP, then I claim that this implies that T is weak type P. And why is that? Well, because if you compute alpha times the measure of the set where TF is greater than alpha, this is alpha P times the integral over omega of the indicator function of that set. But you can control that by TF to the P divided by alpha to the P, because on the set where TF is greater than alpha, TF to the P divided by alpha to the P is greater than 1. And then you cancel the alpha P and you just get the norm of TF in LP to the P. So if T happens to be bounded, then that's it. You get the inequality that defines weak type, with the constant C being exactly the norm of T raised to the power P. So weak type implies strong type. Sometimes boundedness in LP is called strong type for linear maps or sublinear maps, but we'll just focus on linear maps in this course. And weak type is a strictly, in general, weaker property. Okay, so what does Marcinkiewicz interpolation theorem tells us? It tells us that if I have a p in an interval, p0, p1, an open interval, could go all the way to the endpoint, p0 can be 1, p1 can be infinity, and I have a linear map which is weak type p0, p0, and weak type p1, p1, then it extends to a bounded linear map on LP from the dense set S, where it is originally defined. So in order to prove boundedness of a linear map for an entire open range of P, all you have to do is prove at the endpoint, the extreme values of that interval P0 and P1, something weaker than continuity, just weak type. Right? And it's very often used, for instance, by taking P0 equal 1 and P1 equal infinity. So you prove a bound on L infinity of some object, right? It maps bounded measurable functions to bound measurable functions, and you prove weak type 1-1. Very often we don't have strong type 1-1 for sort of typical map that we study and in harmonic analysis or in partial differential equations in particular, or in probability, but very often we do have weak type 1-1, and that's enough to then interpolate and conclude that the maps is genuinely continuous on LP for P strictly above 1. Right, so we'll see an application of that just after to the Riesz projection from Fourier analysis. But first, let's prove Theorem 6.9. This is fairly easy, surprisingly. Let's take an F in the dense set S. So S is a subspace of LP, which is dense. And that's where our map T is originally defined. And then let's try to control the LP norm of T of F. Now, if I raise that to the P, this is equal to the integral 0 to infinity of P alpha to the P minus 1 times the measure of the set where TF is greater than alpha, d alpha, right? This is this usual relationship between LP norms and the measure of sets. Just try to reprove that if you don't have it exactly in mind. Now, what I'm going to do is I'm going to cut F actually into two pieces. One piece where F is large and one piece where it's small. So given alpha, I'm going to define G alpha to be F times the characteristic, the indicator function of the set where F is smaller than alpha. I keep using probabilistic notation because this is really helpful in making the notation gentler or more condensed. So what I mean by that, of course, is the set of all omegas such that F of omega is less or equal than alpha. And H alpha will be where F is large, right? So F is obviously equal to G alpha plus H alpha. So if T of F is large, then either T of G alpha is large or T of H alpha is large, because if they were both small, then and because my map T is linear, I would have that T of F as to be large. So, okay, so this has to be smaller than the set where T of G alpha is greater than alpha over 2 d alpha plus the integral where T of H alpha is greater than alpha over 2. Just repeating myself a little bit. If Tg alpha were to be smaller or equal than alpha over 2 and Th alpha were to be smaller or equal than alpha over 2, then T of F will be smaller than alpha. So I have a containment of that set where it's large into the union of these two sets, and then I use the fact that the measure of the union is smaller than the sum of the measures. Okay, so now I'm going to use my assumptions. So on Tg alpha, I'm going to use the weak type P1, P1, and on H alpha, I'm going to use the weak type P0, P0. So what does that give me? So that gives me P alpha, P minus 1, and then let's introduce an alpha over 2 raised to the power minus P naught. and then P1 multiply by that, use my assumption, so I'm going to pick up a constant, see the constant of the P1 weak type, so it's called that constant C1 times the P1 norm of G alpha raised to the power P1, that's the alpha. And then same thing in the other case, and in the other case I'm getting P alpha P minus 1, I'm introducing alpha over 2 to the minus P naught this time, and I'm picking up a constant C naught times H alpha in P naught norm raised to the power P naught D alpha. Now let's remember what G alpha and H alpha were. So what I have here, making all of this explicit, it's P alpha P minus 1 alpha over 2 to the minus P1, so constant C1, let's put that at the front. And then there's an integral over omega of the indicator function of f being smaller than alpha times f of omega raised to the power P1 d mu omega d alpha. And then I've got the same term with a C naught here, integral 0 to infinity, P alpha, P minus 1, alpha over 2 to the minus P naught, integral of omega, F this time is greater than alpha, F omega, P naught, d mu omega, d alpha. Right, I've just rewritten what this LP naught and LP1 norms are. But now the point is I'm going to exchange the integrals, and I'm going to get C1 times the integral over omega of F omega to the P1 times the integral, okay, alpha is above F of omega, so I'm integrating from F of omega to infinity, P alpha to the P minus 1 times alpha to the minus P1. Let's put the 2 to the P1 here. And this is the alpha, and then the mu omega. Okay. And now I've got the second term, which is C0, 2 over P naught, integral over omega, F omega to the P naught. This may or may not be finite, by the way, but we'll see that this is finite. And this time, on the C naught part, alpha is below F, so what we have is the integral from 0 to F of omega of P alpha, P minus 1 alpha to the minus P naught, d alpha, d mu of omega. Okay, now let's compute these integrals, and what do we get? We get C1 divided by 2P1 integral of omega F omega to the P1. Okay, this is alpha to the P minus P1 minus 1, so I'm going to get P divided by P minus P1, which is positive because P is strictly, which is negative because P is strictly below P1, and now I'm evaluating alpha to the P minus P1 between F of omega and plus infinity. Let's just write up the value directly. This is F of omega raised to the power P minus P1 d mu of omega. And same thing on the second integral, P naught, oh, by the way, there's a minus sign here, so let's minus that. So let's write P1 minus P here. And then here I've got P divided by P minus P naught, which this time is positive, and I get F of omega raised to the power P minus P naught d mu of omega. Okay, and this is certainly smaller than C1 over 2 P1, the maximum, let's say, of, well, actually, no, let's sum them up. But C1 over 2 P1 times P divided by P1 minus P plus C naught over 2 P naught times P divided by P minus P naught, wherever all of that is just a constant as far as we're concerned, times the norm of f in LP raised to the power p. And we've proven exactly that T is bounded on LP, and so it has a unique extension from the dense subset S to LP, with norm at most this constant here to the power 1 upon p. And that concludes the proof of Marcinkiewicz interpolation theorem.